So in what I promise is the last of our discussions on magnetic fields, we're going to look at a loop of wire placed into a magnetic field and then a current passed through that loop. This means that we can create either an electric motor or, as we'll see later, by inverting this system we can actually end up with a generator. So bear in mind some of the things we're going to discuss today will come back when we look at alternating current later on. So if we take a loop here, and this is a conducting loop of wire, and remember our loop does not have to necessarily be circular. A loop is any closed piece of material, and here our loop is a loop that is square in nature. If we pass a current through it and then place it into a uniform magnetic field, the loop will be subject to a torque. Now, what do we really mean by this? What we mean is if we look at this situation here, we have a magnetic field running from the left to the right. A current is then passed through this loop. So here's the direction of the current I, indicated by this arrow. The current will pass through this part of the loop, and subsequently through this part, and this part. Now, as the current passes through this part of the loop, you can see it's moving with the magnetic field. It's parallel to the field. So there will be no force on the moving charges in this part of the loop. As the charges move through this part of the loop and through this part of the loop, the charges will feel a magnetic force acting upon them. That will cause this side of the loop, where the current is going upwards, to be pushed downwards. The force will be into the screen. This side of the loop, where the current is traveling downwards, will cause the force to be upwards out of the screen towards the viewer. That, if we anchor our loop in the middle here, will create a torque, an upwards force here, a downwards force here, and cause this whole armature, this whole loop, to spin around. So if we look at it from the side, here's the force acting downwards here on the moving charges in the loop, part of the loop that's moving into the screen now, and here it's out of the screen, into the screen. That will cause a force upwards here and a force downwards here. That force will vary as the loop spins, but as you can see, it will generate a torque at the center, a twisting force here in the middle. And that's what you need to look at if you're unsure, is go back to mechanics and take a look at the definition of torque. There'll be a couple of points during this slide set where I'll sort of reiterate what torque is from a mechanics point of view, but it might not hurt to take a quick look back at that if you're unsure. And this is just another diagram showing the same thing from a slightly different perspective here. So here's our current running through this loop this way now, and that will cause a force out of the screen here and into the screen here, causing this loop to twist. So when we're dealing with torque, we're defining torque as some magnetic moment times B. It's actually a cross product. So torque, tau here, will be mu cross B and will work for any current carrying loop. In the case we just looked at, a rectangular case. Mu is a vector that's 90 degrees to the area of your loop, and mu takes the form of n I A. Remember the font here, this is an I. So mu is n, the number of turns of wire that you have on your loop, times I, which is the current, times A here, which is the area of your loop. Your current loop in your magnetic field will act like a dipole, and then will have forces acting upon it. So we can write our magnetic dipole moment mu as NIA. That magnetic moment is an SI unit of amp meters squared. So the torque on any current loop due to a magnetic field will be tau. This is the torque. This is mu, NIA, and B. Now, the angle of the loop will vary in the field as it is spun around. So if we look at the torque, we can actually define it as this. Torque will be NIAB sine theta if we're given an angle that our loop sits in the field. And this is a torque, remember, so your units are going to come back in terms of force times a distance, in terms of Newton meters. So when sine theta is a maximum, of course, it will be 1. So torque will be equal to NIAB at that particular point. So the torque twists the loop and the angle will change in the field. And this is the guiding formula for anything where we need to calculate a torque on a loop of current carrying material. And there it is in action. Again, here's the same equation. Essentially, you can relate this to torque itself, which would be force times a distance times sine theta, which, if you actually expand this out, will be equal to IAB sine theta. Here, of course, n is equal to 1 turn. So let's take a look at a couple of examples. This time we'll take a look at a circular loop. It has a radius of 2 centimeters, 10 turns of wire, so N is equal to 10, and carries a current of 3 amps, so I is equal to 3. The axis of the loop makes an angle of 30 degrees with a magnetic field of 0.8 Tesla, and we want to find the magnitude of the torque on the loop. So the magnitude of the torque will basically be mu cross B, which will be mu B sine theta. We know theta is equal to 30 degrees. You could, of course, calculate this all in one piece as NIAB, but I've broken it down. The magnetic moment of the loop will be mu equals NIA. This will be 10 times our 3 amps. And remember, this is area, so this is pi r squared, and this was in centimeters. So it's pi times 0.02 meters squared. This will give us 3.7 times 10 to the minus 2 amp meters squared. Remember, our full equation is going to be mu b sine theta. We know what b is. It was given as 0.8 Tesla. So T now, or torque, tau I should say more accurately, is mu b sine theta, which is 3.77 times 10 to the minus 2, which is our mu value, times b, times sine of 30 degrees, which was the angle our circular loop was lying in the field, which will give us a 1.5 times 10 to the minus 2 Newton meter torque. More examples. So for torque example 2, we're changing things up just a little tiny bit. We've got a circular loop of wire here of radius r, and it has a mass of m, and it's lying on a surface. Then there's a horizontal magnetic field of B applied to this loop. Here's our current I running through the loop, here's our radius, and here's our magnetic field. We assume this is standing on the surface of the Earth. We don't want to get into other planets. So how large can the current I be before one edge of this loop will lift off of the surface? So we pass a current through this ring, through this loop of material, and then we keep increasing I until it lifts up off of this surface. So the question is, how big do we have to make I now for this to levitate? So this means we have 2 torques that we have to take into account. And one of the torques we're dealing with, the torque we actually care about, is from this edge of this loop. We're not going about the center here. This is a loop lying down on the ground. So the torque will be inflicted on this edge of the loop, lifting this side. And that's what we want to find. So there's our magnetic field. Here's our dipole moment here, our magnetic moment mu, which is our NIA basically. Here's our current, here's our gravity acting on the system. So mg will be acting down, mu will be acting up. So how large a current do we need? So what's the magnetic torque acting on the loop? The magnetic torque acting on the loop will be mu b. We only have one loop of material, so n is equal to 1 here. That means mu b is equal to I pi r squared times the magnetic field of B. We do have to now equate this with the gravitational torque, which is keeping this loop flat on the ground. The gravitational torque is just going to be from mechanics, and torque is a force times a distance. So here our force is going to be m times g, mass times gravity for the loop, times the distance r for that loop. What we can do now is equate these two torques. Set I pi r squared b equal to mgr. This will cancel some r's here, and that will leave you with I being mg over pi rb. So we've rearranged for I, we equated this, set it equal to this, and then rearranged it for I. And you'll end up with mg over pi rb. And then you can just simply substitute values in. So this material is best looked at by example. So let's take a look at another one. Here we've got a current of 17 milliamps, so 17 times 10 to the minus 3 amps. And that's maintained in a single circular loop, so n equals 1, with a circumference of 2 meters. A magnetic field of 0.8 Tesla is then directed parallel to the plane of the loop. What is the torque exerted by the magnetic field on the loop? Well, torque exerted by a magnetic field should be immediately nbi sine theta. We can throw n away as being 1. The magnetic field is parallel, so theta is 90 here. So what is the magnitude of the torque exerted on the loop? Well, the cross-sectional area of the loop is something we don't have. So we're going to say this is 2 pi r, which is basically equal to 2m. So r is c over 2 pi. This is 2 over 2 pi, and basically becomes pi over m over pi. I apologize. So we'll end up with 0.318